style, yo. I breaks it down to the bone gristle. Ill speaking, scud missile, heat seeking. Johnny blazing, nightmares like Wes Craven. Niggas gunning, my third eye seen it coming before it happened. You know about them fucking stats.
Hello, and welcome to the video on parametrized surfaces. So let's get started. So for a parametrized surface, first of all, what a surface looks like is, surface I'm talking about is in 3 dimensions. And it looks, again, you've probably seen this before, like the whole flying carpet thing. And it's a surface in 3 dimensions. Here's our x, here's our y, and here's our z axes. So this is our surface, right? It looks something like that. It's kind of curvy, and these vary, right? So anyways, this is our surface. Let's say it's S, and what we're going to do to it is parametrize it, which means that we're going to give it a name based on 2 variables, u and v. So technically, as it exists here in the 3D space of x, y, and z, what this is going to look like is the following: x of u and v, y of u and v, and z of u, and v. Okay, so right now, this might look a bit confusing, like what are all these u's and v's for? But basically what we have is, this is our final product, but what we're starting with is something in the u-v plane. Okay, so u and v could be any variables. U and v are called our parametrizing variables. So they are in what's called the parameter domain. And we'll just call it D. Okay. So these are our variables, and let's say u goes from 0 to something else, some interval, and v goes from something to something else. Okay, so up to some value like b or something. From 0, u goes from 0 to a, and v goes from 0 to b, and you get this square here, right? And basically what G does is take all of these values in here, this blanket here, this very like flat square, right? And it maps it to, a point in the XYZ space, right? It maps each one of these points to something in the XYZ space and makes this flat square into a blanket that covers a surface, okay? Which actually is the surface itself. So essentially what we did here is take these 2 variables, u and v, and each of the x coordinate, the y coordinate, and the z coordinate depend separately in some way on these u and v to create this surface that we see here. So this G takes this 2D, this flat 2D UV plane, so this is the UV plane here, and it maps it to, so through G of UV, it takes it into the XYZ 3D space. Okay? So that's essentially what parametrizing is. Parametrizing in general is kind of just like using variables to represent other things. So u and v are parametrizing variables here. Okay, so an example of this, just a quick example, is like G of uv equals something like u squared, and then u plus v, and then 2v. Okay, so in this case, the first coordinate is going to be our x, second coordinate is our y, and the third coordinate is our z. Alright, so see how these are dependent on some kind of combination of u and v, right? Okay, so that's just an example there. Now we'll go into more specific examples that you might see. So the first is a cylinder. So cylinder. So what a cylinder is, conceptually, is, well, first of all, I'll just draw a little picture of it. So we have our x, y, and z, x, y, and z planes, and we have some kind of circular thing. I always think of cylinders as like cans, like tomato can or something like that, you know, or a Pringles can. This looks more like a Pringles can. So cylinders like that, right? And if you think about the surface of the cylinder, it's basically just like the circle here on the xy plane. It's just repeating that same exact circle at varying heights, right? The same exact circle. Okay? So, in this case, I'm going to call our circle, I'll name it with the following equation. X squared plus y squared equals some random r squared, okay, where r is our constant, r is the radius, so r is a constant radius, okay, so essentially this cannot be a parameterizing variable because it is constant and not a variable, okay, so r is just going to stay the same, but these are x and y, those are the ones that are variable. But basically what we can do here is not use x and y directly, but we can take advantage of polar coordinates, okay? So basically these points on the cylinder, so points on the cylinder, I'll say on cylindrical surface, right? Because we're looking just at the surface, not like the Pringles inside the can, we're just looking at the can itself, okay? So the points on the cylindrical surface have the following coordinates. They have coordinates of r and theta and z. Okay, so basically, I'll just write down what the parameterization is, and then I'll explain it after that. So these are our parameterizing variables because they change, right? They are variable, they're not a constant. And what this is going to look like is r cosine theta, r sine theta, and then rz. Okay, so this is the cylindrical parameterization, I guess you could consider it. And so again, you might recognize these from like polar coordinates, right? How our x equals r cosine theta, y equals r sine theta, and z is just z in cylindrical coordinates. Okay, so this might be familiar anyways from cylindrical coordinates. And then again, just to reiterate, or maybe from previous experience and knowledge, the theta is we're going all the way around each circle, right? So that would be from 0 up to 2 pi. And then the z just goes from whatever bounds you set, if it's like from 0 to 2 or whatever. But right now I'm just going to write, hold on, let me back up here a little bit. So z goes from negative infinity to infinity. So this is an infinite Pringles can. But usually you'll have bounds on z, such as, like I said, 0 to 2 or something. Okay? Alright, so now on to the next kind of parameterization. And this is the sphere, the all-important sphere. Okay, so for a sphere, that looks like, hold on, let me sketch a little thing here. So we have x, y, and z. And let's say our circle goes like something like this. Okay, and then we have it going around, and it's centered at the origin. Okay, and something like that. That actually turned out pretty well. So anyways, it's a sketchy sphere. And so for a sphere, now we're going to be dealing with spherical coordinates. And again, our radius, since we're looking just at the outside of the sphere, like the surface, right? Not the inside. We don't care what's on the inside. But when we're just looking at the surface, any point that you go to on the surface has radius r. So again, capital R, I'm going to say, is our constant radius. So that is constant and therefore not a variable, so constant radius. So that means that the only thing that can vary, that's left to vary, are theta, which exists on the xy plane, right? How much you're rotating around on the xy plane. So this is theta. So r is a variable, that's a parameterizing variable. And the other one in spherical is called phi. Okay, and that's measured from up here. So at the top, when you're going along the z-axis, that's when phi equals 0. And then we're going to go down. This is our angle here. And we're going to go down, 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 down. And when you get to the bottom, to the negative z-axis, this is when phi equals pi. Okay? And just for theta, to clarify, when you're on the x-axis, theta equals 0. And then as you go around all the way to the negative x-axis, then you get that it equals pi. But here I'll label it as pi over 2, right? So again, sorry if the last part was confusing, but x, when you're on the x-axis, theta equals 0, as we know, right? Working in polar coordinates. And then you're going around, and I just labeled the 90 here, just to show you that theta exists on the xy plane. Okay? All right, so we also have, so that was theta, and this is phi. Wow, that's big. And so these are our parametrizing variables. So these are our variables. And the parameterization looks like the following. We've seen this in spherical before, so don't get too scared by it. So we have our r, and then cosine theta sine phi, r sine theta sine phi, and r cosine phi. Okay, so that is a handful, I will admit, but this is like, once you do problems over and over and you get more practice with them, you'll become more familiar and it'll hopefully come naturally to you. Okay, and now one last parameterization. So then we have, so we went over cylindrical and spherical. Those are the two main ones. And then we also have just a general graph of z equals f of x comma y. So what this means is that when you're writing your parameterization, so we have g dependent on x and y. These are like our u and v. Okay, they just happen to be x and y. But in this case, what this is going to be is x is going to be x, y is going to be y, and z now, we're going to plug this into the z spot. That was a really weird arrow. Okay, so we're going to have our f of x comma y there. Okay, so this is our z, and this is our y, and that's our, not z, that is our x. Okay, so x corresponds to x, y to y, and z to whatever the function, the given function is. Okay, and in this case, as I said, our u and v are x and y, so x and y are our parameter variables. Okay, so that was just a brief overview of parametrized surfaces, and in another video we'll be going over surface integrals and how we use these parametrized surfaces.
I keeps it moving, know just what the fuck I'm doing. Rap insomniac, fiend to catch a nigga snoozing. Slip the cardiac, arrest me. Exorcist hip hop possess me. Crunch a nigga like a nest.